Hello, everyone. I hope you're all healthy and well. Welcome to our next talk in the Golden Webinars in Astrophysics series. Our speaker today is Adam Frank, who is the Helen Fred Gowen Professor of Physics and Astronomy at the University of Rochester. My name is Thomas Puzia, and together with Simon Angel, we have organized today's webinar for you. As you know from our previous webinars, most certainly, we always provide interpretation into the Spanish language, which is already done by Mr. Patricio González, who is translating for us in the background into Spanish. En sus dispositivos pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación que se encuentra abajo en la aplicación Zoom y obviamente seleccionar español. If you have any questions during the talk, please type them in the Q&A window. You can also upvote the questions and comment on them, and we will then select the best questions and comments for the discussion after the talk. Would I like also to acknowledge the generous support of the Center for Astrophysics and Related Technologies, also known as CATA for its Spanish acronym, for supporting this series.
Let's begin then with a short introduction of our panel members who are with us today. We have Adam Frank, our speaker, Patricio González, our interpreter, Thomas Puzia, co-host and faculty at the Institute, and myself, Simon Angel, co-host and researcher at the Institute. From the Institute of Astrophysics at PUC, we have Tulia Siliotto, master student of the Institute, and Franz Bauer, who is a faculty member of the Institute. We also have the great pleasure to welcome our guest panelists today. We have Sarah Seeger, class of 1941 professor of planetary science, physics, and aerospace engineering at the Massachusetts Institute of Technology. Abel Mendez, planetary astrobiologist and director of the Planetary Habitability Laboratory at the University of Puerto Rico at Arecibo. Paul Heunigen-Hühne, professor of philosophy in the Institute of Philosophy at the Leibniz University Hanover, Germany, and lecturer at the Department of Economics at Universität Zurich. Michael Strauss, professor of astrophysical sciences at the Department of Astrophysical Sciences of Princeton University. Pavel Krupa, professor of astrophysics at the University of Bonn and the Charles University in Prague. Hans Sineca, astronomer emeritus, ex-deputy director of the Sophia Science Center at NASA Ames. And Joel Primack, distinguished professor of physics emeritus at the University of California in Santa Cruz. Last but not least, we have our excellent Q&A manager, Ricardo Acevedo.
So it is our great pleasure to introduce Adam Frank as our Golden Webinar speaker this week. Adam has attended University of Colorado for his undergraduate work and received his PhD from the University of Washington. He held postdoctoral positions at Leiden University in the Netherlands and at the University of Minnesota afterwards. In 1995, Frank was awarded the Hubble Fellowship. And in 1996, he joined the faculty at the University of Rochester, where he has been professor of astrophysics ever since. Adam studies the processes that shape the formation and death of stars and has become a leading expert in the final stages of the evolution of stars, similar to our sun. Most of his studies employ regular and magnetohydrodynamics applied to astrophysical environments. His research group has developed the AstroBear adaptive mesh refinement code used for simulating MHD systems in various astrophysical contexts. Recently, he has also been interested in studies of planetary atmospheres and habitability in the context of astrobiology. So now, without further ado, we would like to hand over to Adam, who will give a little talk about aliens, life in the universe, the search for technosignatures, and why all this is pretty important for Earth's future. Adam, it's a great pleasure.
Thank you so much. Shall I share my?
Please go ahead.
Screen. Okay, here we go. All right, and we'll start that. Hopefully that all works. And now
looks great.
Good. Okay. Okay, so thank you very much for the opportunity to talk today. I'm very excited about this and very honored for the chance to talk. It's quite a roster of people who've given these talks. I have very excited. I have a lot to tell you about. I have way too many slides, so I'm going to be merciful to all of us And I'm going to talk for about an hour, and then I'll stop no matter where I've gotten in my slide deck. So let me start my little timer here. So, okay, so the title of the talk is A Little Talk About Aliens. It takes a cosmic village to do these kinds of studies. So these are the list of my collaborators and people I've been working with on this. I particularly want to note Jonathan Carroll Nellenbach, who's been my collaborator for many, many years on projects like this. And I want to note if you see an asterisk here, it means someone who is either a student or a postdoc. So this NASA-CATS collaboration, I will tell you a little bit more about as we go on. So for a talk like this, it is good to have a table of contents. So where we're going to go with this talk, first we're going to do a wee history, what I will call the heroic age of SETI. And then we're going to talk about the entrance of astrobiology into all of this, what I call the 3 revolutions of astrobiology, and how it's changed our understanding of aliens, intelligent or otherwise. Then we're going to talk about biosignatures, because you can't really talk about technosignatures, which I will say is the modern version of SETI, without talking about biosignatures. Then we're going to talk about technosignatures and a little bit of just the history, the really remarkable history that has happened just over the last 5 years in this field. And then we're going to conclude with why it matters, why it actually, these kinds of questions that we're going to ask reflect back on us in this particularly perilous moment in human history. And then we'll end with some closing thoughts. Okay, so let us begin with a wee history of astrobiology and SETI. This question of life in the universe is ancient. You can see many cultures debating it going quite a ways back, including the Greeks, where there was, for example, Aristotle, who held that there could not be many worlds. Earth was unique. It was the only planet really that mattered. It was the only place really where you could have life and was in fact a world. And then you had people like Democritus, who, this quote here, "There are infinite worlds, both like and unlike our own. In all worlds, there are living creatures and plants and other things we see in this world." So you see already 2,500 years ago, this basic debate between optimists and pessimists taking shape. In the age of science and the Enlightenment, this became what is known as the many worlds debate. And there was this wonderful book, Conversations on the Plurality of Worlds by de Fontenelle. And this is a front piece from it showing, this idea that there were many, many worlds. He was an advocate for the fact that there were many other worlds and many of them would be inhabited. And then by the beginning of the last century, I think I spelled origin wrong there, the origin of life studies became where there was an introduction of scientists beginning to really think about this in some systematic way. There was J.B.S. Haldane, who coined the term abiogenesis, and certainly the idea of the primordial soup. And then in the 1950s, there was the famous Miller-Urey experiment, illustrated here, which showed that, with even very simple kinds of initial conditions, you could at least get the amino acids that were essential for life on Earth. So that seemed to indicate that perhaps getting life started might not be very difficult. Now, the main focus of our talk today is going to be intelligent life. And so that brings us to the beginning of the question of intelligent life in the universe. And I would say the scientific formulation of the problem begins in 1950 by mistake with the famous lunch at Los Alamos with Enrico Fermi, and who was a super genius, along with some compatriots. And they were walking towards the cantina at Los Alamos, and there'd been this cartoon that I'm showing in the New Yorker using UFOs to explain the missing trash cans in New York City. And that, like good scientists, that got them started on a discussion about things moving faster than light, or at least moving at light speed. How fast could a interstellar spaceship move? And the conversation went along this ways, and then moved on to other topics. And then about an hour later, over lunch, Fermi just sort of pops up and asks this question, but where are they? The famous question, where are they? And this would later get formulated as the Fermi paradox. If intelligent life, technological life, is common, then why haven't they crossed to the galaxy? Fermi had done this calculation in his head and recognized that it would not take very long for a star-faring civilization to pretty much cross the entire galaxy, and they should be here already. So his question was, but where are they? The next big step for SETI was Project Ozma by Frank Drake, who was amazingly a new hire at Green Bank Radio Observatory and managed to convince his colleagues to undertake a search of nearby sun-like stars for signals that would be artificial, that could be interpreted as coming from intelligence. Now, he made no detection, but he did get lots of attention. The media really picked up on this, and this was the formal beginning of SETI. Now, after that, Drake spent the next year looking over his shoulder, looking for who was snickering, laughing behind his back. But instead, he got a phone call from the government, which was in the National Academy of Sciences, which wanted him to lead a meeting on interstellar communications. And so he put together a meeting. This list here are of the people who attended. There's Carl Sagan, a very young, ambitious Carl Sagan showing up at this meeting. And the most important result of this three-day meeting was the Drake equation, the famous Drake equation, which Drake really put together just as a way of, it was really an agenda for the meeting. And the famous Drake equation, the idea of it is Drake wanted to know, how do we even ask the question of how many civilizations there are out there to communicate with? That's this capital N. And he broke the problem up into a number of terms: R star, the number of stars forming in the galaxy; F sub p, the fraction of those stars that have planets; N sub E, the number of planets in the habitable zone, the planets that could have life on them; the F sub L, the fraction of that life, the fraction of those planets that go on to form life; F sub I, the fraction of that planet, that life that goes on to become intelligent; F sub T, the fraction of those intelligent species that develop technology; and then finally, what I like to call the final factor, L, the lifetime of the civilizations. So that was a milestone in thinking about intelligent life in the universe. Now, other things which we're going to come back to, we're going to see these seminal ideas which still get talked about, was the idea of Freeman Dyson proposes that one way a civilization might evolve, a technological civilization, will be to encircle their star or surround their star with basically a giant machine, a Dyson sphere as it was called, that would capture all of the sunlight that could then be put to use for building their interplanetary or even interstellar civilization. So Dyson spheres were another important idea that we're going to come back to. Then came what was known as the Kardashev scale. Kardashev was a Russian physicist, and his idea, he was really interested in detection, trying to understand like what kinds of civilizations might you be able to detect. But in the process, he ended up coming up with this scale for how civilizations would evolve. So we had a type 1 civilization in which all of the power falling on a planet would be put to use by the civilization. Type 2, all the power available from the star itself would be put to use for civilization. And that was really kind of a Dyson sphere. And then finally, a type 3, where all the power available from the home galaxy would be put to use. So the Kardashev scale is an idea that becomes quite important in the development of thinking about the trajectory of civilizations. Because to do SETI, you have to think about the evolution of life and then the long-term evolution of civilizations. In the 1970s, we get the second generation of SETI pioneers. There are meetings, SETI continues, there are many meetings and plans for searches, and a new group of researchers join the effort. There's in many ways, most importantly, Jill Tarter, but also Woody Sullivan, Seth Shostak, and many more. And Jill really needs, at some point in the future, there will be statues to Jill, because when you think about the difficulties that women continue to face in science, that at the time, as a young woman scientist, that she would take on such a radical proposal as to search for intelligent life in the universe. Just the courage that she has exhibited and the resiliency and the good-naturedness across her career is something that's really extraordinary. Now, as these ideas evolve, as time goes on, you see a number of important ideas coming into play, one of which is this paper by Hart in the 1970s, which really formalizes the Fermi paradox and the idea that we don't see any aliens here. We see no spaceships here now. Therefore, what he said was there are no aliens. That was a direct version of the Fermi paradox. Why aren't they here now? But then also, as Radio SETI evolved, we had people beginning to talk about an indirect Fermi paradox. And there was a claim that, okay, we've done searches and we haven't found anything. Therefore, can we already say that there's no intelligent life in the universe? And this was a term that David Brin coined, the great silence, that we're listening and we don't hear for anything. And from this came another important idea, the great filter, that the idea was that the great silence implied that something must hold the evolution of civilizations back. There's either it's hard to get to intelligence, or once you form intelligence, it's hard to go on to form a technological civilization. And we're going to come back to that idea as well. So then by the time we get, as the 70s go on, what I'm going to call classic SETI continues to evolve. And there is plans to build, enormous receivers that could detect faint signals from intelligent civilizations. The emphasis here is very much on radio, because radio can you can see across the entire galaxy or further, because it's using long wavelengths. Now, everyone recognized this was a challenging search, and that's because really you didn't know exactly where to look, you didn't know exactly when to look, you didn't know what frequencies to look at, and you really weren't sure what to look for. So that's why there was this emphasis on purposeful beacons. What for classic SETI, I'm going to distinguish classic SETI as having this emphasis on looking for someone out there setting up a beacon and often trying to communicate. There was this real emphasis on interstellar communications. And I'm going to distinguish that to what's happening now, where really we don't really need to think about communications anymore. And we can think about indirect detections. Now, there was some of that happening then, but there was overall this sense that we needed to look for beacons and we needed to be interested in communications. Excuse me. Okay, so what happens? Well, basically for NASA, SETI gets killed because of what we like to call the giggle factor, right? So in 1978, Senator William Proxmire gives NASA his Golden Fleece Award, which he awarded to government projects that he thought were fleecing the American tax dollar. And, SETI was an easy, little green men, it was an easy target. So after that, NASA is really kind of not allowed to fund SETI for a while. But then that kind of calmed down. NASA tries again in the 1990s, and again it becomes a political football. So there's this quote from NASA, from Congressman Conte: "Why spend millions on SETI when for 75 cents I can buy a tabloid and see pictures of aliens?" Right. So that was the kind of thought. And so once again, NASA becomes kind of gun shy for good reason about trying to propose SETI, and so the funding for SETI pretty much dries up, other than private factors or private donors. But nature and science had other plans. And so now let's sort of turn to the three revolutions, what I like to call the three revolutions of astrobiology, which, are really going to be starting in the 1990s. I mean, it goes beforehand, but, these really began to take off in the 1990s. So the first and perhaps most important is what I like to call the exoplanet revolution. The first exoplanet orbiting a sun-like star is discovered in 1995. And by now we're over 4,000 detected planets. So this is this lovely plot. You'll see versions of this where we're looking at the size of the planet that has been detected versus its orbital period in days. Remember that the Earth has approximately 300-day orbit. And what you see is we've discovered lots of different planets, and we've discovered lots of different kinds of planets. We have Jupiters that are parked right next to their star. We've got ocean worlds and ice giants. We've got Earth-like worlds that are so close to their star that they're basically molten. And we have all different kinds of rocky planets. And of course, we also found that the most common type of planet in the universe is one that's not in our solar system, a super Earth, a planet with a mass between Earth and Neptune. And it was really the Kepler mission that sort of blew the doors off this. And here's William Baraki, who deserves his own story, just his unwillingness to ever give up on the idea of transits, of being able to do transits en masse. And so the Kepler mission was very, very important to sort of really being able to do wholesale exoplanet detection. And now what we have is we have lots of exoplanets that we've discovered that are in what's called the habitable zone, the very important region where liquid water can exist on the surface. And we can argue about whether or not the habitable zone is the only way to look for things. It's clear there's other possibilities, but it's been an important guiding idea in the search for life in the universe. So we now know of many planets in the habitable zones. Now, it's interesting to note that what SETI gave for this in particular, because there were these two very important meetings that were driven by the SETI community in 1978 and 1979, assessing what techniques we should use to try and detect exoplanets. And so at these meetings, astrometry, radial velocity, direct detection, all of these different methods were assessed, and directions forward were given. And it's funny that transits were considered not to be a good idea for this. Then, of course, we realized that transits were the best way, or one of the best ways to do this. So that's why Bill Baraki was such a hero in the end. Okay, the other revolution that we need to note is our solar system studies. We've now visited every type of planet in the solar system. And from that, we've learned amazing things about how planets function, including things like Mars may have been a blue world at some point. We know that there was liquid water on Mars during an early period of its evolution. So we've seen quite a bit about how planets evolve from our studies of the solar system. And then finally, studies of the Earth's long history itself. So for example, I like to always ask people, which one of these 6 planets is the Earth? And the answer is all of them. This is Earth during different phases of its evolution. It was a molten world early on. The continents took a while, so it was to form. So it was actually a water world. It's been so hot, at some points it's been a jungle world. There have been snowball Earth phases where the planet was almost entirely covered in snow. Here's the planet now, and then in the future, the oceans will be boiled off. So, the Earth has been many planets, and the evolution of the Earth has been really shaped by its life. And so we get to see from Earth's history how life and the planet co-evolve. So the third revolution is Earth's deep history. And the best example of life and the planet co-evolving is what's called the Great Oxidation Event. What's remarkable about Earth's history is that if you visited Earth 3 billion years ago, a time when there was already a lot of life, there was already a biosphere, and you landed and stepped outside of your spaceship, the first thing that would happen is that you would die from asphyxiation because there was no oxygen in the atmosphere, or very little. And it was only the Great Oxidation Event, it was only that formed, and it was basically life, a new version of photosynthesis that was invented by life, that actually put that oxygen into the atmosphere. It was photosynthesis breaking water apart and dumping the oxygen back into the atmosphere that gave us the oxygen-rich atmosphere. So that is the example of the co-evolution between the biosphere and the other geophysical spheres. Now, what does this change for? What do these revolutions change for thinking about life, and particularly exo-civilizations, as I'll call them? Well, it gives us new data for the Drake equation, right? In particular, the fraction of the fraction of stars that have planets, and the number of planets in the habitable zone. We now know these numbers, and its FP is approximately 1, and NE is approximately 1/5. So every star you see in the sky has a family of worlds. That is such a radical change in our understanding of the nature of the universe. And if you count up 5 of those stars, one of them is going to have a planet in the right place for life to form. Now, this allows us to play a little game here. You can actually, this is some work that Woody Sullivan and I did in 2016. You can count up the number of habitable zone planets in the universe, in the observable universe, and that turns out to be 10 to the 22, or 10 billion trillion. And that number tells you how many experiments nature has been able to run in creating life and creating technological civilizations. So the only way for us to be the only civilization that has ever formed in the entire history of the universe is that the odds of having all that evolution happen correctly must be less than 1 in 10 billion trillion, or 10 to the minus 22. And that's entirely possible, but if that's true, then that sort of indicates that nature is quite biased against having happen what has happened here. So I like to think, we call this the pessimism line. As long as you're greater than 10 to the minus 22 per habitable zone planet, then somewhere else what's happened here has happened. Okay, so how does the exoplanet revolution change how we think about life, and in particularly intelligent life? Well, first of all, we know exactly where to look now. We know where the planets are. We know exactly what kind of planets we should be looking at in terms of those in the habitable zone. And we're also learning what exactly to look for when we look for life. And that brings us to biosignatures. Okay, so we're going to spend a little time here talking about this field of biosignatures. So what is a biosignature? Essentially, it's the imprint of an exobiosphere, meaning a biosphere on another planet, in atmospheric chemicals that you can detect via spectroscopy. So here's this lovely figure from a magazine. And what happens is, during a transit, when a planet passes in front of a star, there is a little bit of time where light from the star is actually passing through the thin veil of the atmosphere of the planet. And then if you look at the light that is from the starlight that passes through the atmosphere, there will be the imprint of the spectral imprint of chemicals that were in the atmosphere. So things perhaps like methyl chloride, methyl bromide, isoprene, dimethyl sulfide, all of these chemicals, which we think are very important for life, or that we think that could only be in an atmosphere if life were, at least our kind of life, were in that atmosphere. So that is what a biosignature is. And we now have the technology already to do what we call atmospheric characterization. We can already look at spectra from planetary atmospheres. Now, doing it with the kind of resolution to get biosignatures, that we're just developing the capacities with JWST and the next generations of telescopes that we're designing. So what's interesting about biosignatures is that we expect them to change through time. So here is the spectra from the Earth at different phases of its evolution, from the Archean very early on, 3 billion years ago, to the Proterozoic Earth, to the modern Earth. And you can see that the kinds of spectra, the kinds of spectral signatures change. You go from lots of methane to then having lots more water, and lots more, and oxygen as well, molecular oxygen, indicative of the great oxidation event. So this is really it. We're now learning to sort of understand, to see what kinds of chemical imprints we would expect from biospheres at different phases of their evolution. And that is where we're going to tune our searches as our future searches. Now, here I'll talk about the rise of biosignature science, because now this is really, there's a large part of astronomy right now which is dedicated to understanding what biosignatures we should look for, how we should look for them. This is, for example, a biomass-based model to estimate the plausibility of exoplanet Seeger. These are two examples of survey papers that have actually, we're now at the point where we have survey papers looking at the field. And so the field has developed to the point where we're really becoming more sophisticated about asking our questions. So we need to understand, in doing biosignature science, what does life produce in terms of the chemicals? How could we be fooled by a dead planet? Our data is always going to be limited, how we will interpret that limited data. And how will we also quantify our uncertainties or our certainties? So, the point I'm making here is that biosignature science now is becoming very well developed. And it's also, people always say, well, you're looking for Earth-based life. What if it's not Earth-based life? Well, lots of smart people, like Sarah Seeger, have looked at this and thought about this. And so there's a whole move now to be agnostic about our biosignatures. Rather than looking for what Earth life has produced, can we think about the problem in terms of like, well, what would life in general do? And what kinds of things would it dump into an atmosphere? So Sarah worked on the, I think she called it the small molecules project, which I really liked. You just look for, you know, what kinds of small molecules might life anywhere use in its biochemistry, and how that might, what kind of biosignatures would that lead to? Another approach, which I'm very fond of, is the idea of doing a kind of statistical planetary systems biogeochemistry. And this is the front piece from a grant that University of Rochester was part of, led by Sarah Walker. And the idea here is to look for statistical or topological measures in the chemical networks that life produces. And this is a very different kind of approach. The quote here would be, a molecule by itself is not a biosignature. It's all of the molecules and their relationship to each other that you would find in an atmosphere. So this is a network theory approach. And the way this works very briefly is, here's a network. These could be 3 chemicals. And the links here between them are the fact that the chemicals will react with each other. So, each node in the network has links to other nodes, and we call that a degree. The number of links that that each node has is the degree of that node. And if you have a complicated network like this one up here, what you can do is you can do the statistics of that and ask, on average, how many, what is the degree, or how many links does each node in it, or what is the shape of the distribution of links or degree in that network? And you can use this now to do an agnostic approach to biochemistry. So for example, there's this paper by Kim et al., where they were asking, are there universal properties of biological networks across scales? And they were looking at scales in terms of scales on the Earth. So like from an organism, so we go down and we look at, I won't go into this plot very much, but if you look at the bottom here, you see the idea of a chemical network for an individual, a chemical network for biosystems, the chemical networks for the biosphere, and then you compare that to just a random chemical network. You just randomly hook up chemical reactions. And it turns out that the chemical networks for biology are very different from random networks. And also the properties of the statistical properties of those networks look similar from individual to ecosystem to biosphere, indicating perhaps that life was using sort of universal properties, universal principles in building its networks, whether it was for a cell, of an ecosystem or the entire biosphere. And then finally, I'm not going to talk about this plot or this very much. We could talk about later if someone wants. But also, biosignature science now is also getting very sophisticated in its statistical interpretation of the data in terms of using Bayesian frameworks, where you really are going to ask, like, okay, what are your priors that come into this? For each observation, you have some data. You want to know whether or not that data allows you to conclude that you're actually seeing biology on a planet. So the idea of just finding molecular oxygen and saying, "Yay, we found life," the field has gotten past that. Okay, so that's biosignatures, and the emphasis I really want to make here is that as we now move to technosignatures, it's really just an extension of biosignatures, right? It's the same kind of science, but we're just looking for now evidence not just of a biological activity, but of technological activity. So again, as we saw, NASA had this was put in a position where it was difficult for it to fund any kind of searches for intelligent life or technological life. But the field of astrobiology was being very well funded. So at some point it became a little crazy that there was lots of funding for searching for quote unquote dumb life. And I don't mean to be putting microbes down for that. But why would you do that and be like, well, no, we can't ever look for intelligent life? So, i.e. technosignatures. And it was Jill Tarter who coined the term technosignatures in response to what was happening in the biosignature community. And then, remarkably, in 2018, Congress actually added to the budget, directing NASA. It told NASA that it should spend like $10 million for technosignature study. And all of a sudden NASA was like, oh, okay, what should that look like? And they convened this meeting in 2018 in Houston to gathered scientists to ask, like, okay, if we were going to fund this, what would we do? And I was lucky to be at that meeting, and it was just, everybody was giddy with the idea, like, wow, okay, what would we do? And it was the beginning of really, I would say, the modern era, the beginning of the Renaissance of technosignature studies. Now, nobody was given $10 million, but it did begin the new era. And also, we have to note the Breakthrough Listen initiative, where millions of dollars were given for the kind of classic radio search. So together, the Breakthrough Listen and then NASA beginning to talk about technosignatures was really the beginning of this new era. So out of that meeting came things like the beginning of systematic thinking about technosignatures. So this lovely paper by Sophia Sheik from 2019, she was a graduate student. She attended the meeting, but she put together this paper. And so she thought, like, okay, how do we decide what kind of technosignatures should we look for? Because the thing about the literature was that the literature was all over the place. Sometimes it was just in conference proceedings. A lot of it was in the gray literature. And it was lots of people just throwing out ideas like, well, aliens could do this, aliens could do that. And so, okay, now we need to sort through those and decide what's worth looking at. And so she came up with this lovely sort of figure of, or axes of merit. So if somebody proposes a technosignature to you, you want to ask, can it be done now or can it be done in the future? Is it costly? Is it cheap? Is it information poor or information rich? Is it a short-lived technosignature or a long-lived technosignature? So this was like the beginning, as we're going to see, of really trying to systematize this field, the way the biosignature community had been doing for about 20 years, of systematically thinking through their proposals for what kinds of search to be done. And then, remarkably, NASA began funding technosignatures. So I was the PI of a 2019 proposal, and we purposely did this proposal, made it sort of short and small. It was 2 years, but it was multi-institutional. And the idea was to develop a library of atmospheric technosignatures. So we called the grant, or the program, our group, CATS, Characterizing Atmospheric Technosignatures. And so, the Cheshire Cat is, I sort of like to think about as the mascot of our group, because, what are you going to see? We're going to see the smile on the cat, which is the technosignature, which implies the existence of the technosphere. And we're going to talk more about that idea of technospheres. And then happily in 2022, this grant, we got it renewed for 3 years with a much larger budget. So we're really going to be able to do some interesting work. So now I want to talk about technosignatures and the work that has been done. And anytime you see the little Cheshire Cat, that means work that has come out of the group, either directly or from people in the group. Okay, so what are examples of technosignatures? What I'm showing here is a ICAR proposal that Jason Wright led that had a number of different groups, including the University of Rochester. This was not funded, but hopefully the next time go around, we might be able to get a chance to do it. And the things we were proposing here were things like looking for heat islands or city lights, looking for the large-scale deployment of solar panels on a planet, looking for atmospheric pollutants like chlorofluorocarbons, looking for orbiting megastructures like a Dyson sphere or a Dyson swarm, and then even looking in the solar system for the possibility that, someone was here a long time ago and left something. And this brings up the idea of lurkers, which we can talk about later. But all of these are possible technosignatures, and a number of these were in our proposal. And now let me talk about them, some of them, in a little bit more detail. Okay, so the one that really captured the public attention was the alien megastructures, right? And so this came from Voyager's star. So this was a star that had Kepler data, had transit data for, but it didn't behave at all like any planet that we knew of. Instead of nice, smooth transit, it was just a number of, chaotic, not often repeating signatures or transits. This is basically starlight versus time. And you can see the starlight being blotted out again and again in very strange ways. And when the paper on this was written, one of the things they considered, they talked about astronomical things like swarms of dust or comets, but they put in the possibility that, well, these could be large-scale structures orbiting the star that are blotting out the light, as if someone had built not a Dyson sphere, but really a Dyson swarm, say, large scale solar collecting satellites. And then this got picked up, and there was an article in the Atlantic about this, and it just sort of blew up in the press, and this became quite popular to discuss. Now, it turns out that for Boyajian star, it's actually the best explanation is dust, which is fine because of course, we're going to look at all the other possibilities before we would claim that it's a technosignature. But what was important about that paper was the first paper where a technosignature was listed as one of the possibilities, and the referee didn't just throw it out, right? So this was the opening of being like, look, if we're going to look at planets, we're going to see things we sometimes don't understand, and you can't say you're not allowed to include the possibilities of technosignature. So this was sort of broke the dam in many ways. Now, another one that I think is really interesting is the idea of city lights or heat islands. So there are telescopes on the drawing boards now that may actually be able to resolve features on exoplanet surfaces, that may be able to do kind of a tomography of an exoplanet. So this is by this wonderful paper by Bergdugina and Kuhn in 2018, where they used data from, they did synthetic modeling of the extremely large telescopes, or even larger telescopes, the next generation of telescope, to understand what you might be able to do if you looked at Earth from a distance. If this is your actual continental map, with including, I think this was heat islands from industry. No, I think actually, I'm not sure exactly in this map what the purple is here. But what was important was that the recovered map from the telescope, you could get a feeling, some idea of what the continents looked like, what the topology of it was. And in a different figure, they also showed if you had heat islands from industry or large scale deployment of lights, you might be able to make these out in such a map. So that's important. So, the actual activity on a surface is something that in the next, 10, 20, 30, 40 years, we might be able to begin to detect as a technosignature. And there was this recent paper on the detectability of night side city lights on exoplanets by Thomas Beattie. And here's this quote from it: "The known planet Proxima b is a particularly compelling target for LUVOIR A, which was a proposed large orbiting large space telescope. And that it would be able to detect city lights 12 times that of Earth in about 300 hours. And so this is an urbanization level that is expected to occur on Earth around the mid-22nd century. So this was another study using a proposed telescope that showed that, yeah, city lights, if you had a much larger kind of deployment of city lights on a planet, perhaps a Trantor-like city or Trantor-like world, that would actually, Trantor is the city planet from the Foundation series, but that would be detectable, that we're actually on the edge now of being able to detect these kinds of technosignatures. Now, I also want to note here, you'll notice none of this is about communication. We're not asking whether or not they're sending us signals. We are in fact looking for what I would call metabolic technosignatures. We're looking for the consequences of having a civilization, of using energy to create and maintain your civilization. So another possibility along these lines is seeing the large-scale deployment of solar energy collectors. So if you use solar panels of any type, depending, wouldn't really matter what kind of material you were using, there will be a UV reflectance edge. There will be an imprint in the reflectance of the light from the star. It'll have an edge in it, much like the red edge, which we think plants impose on the reflectance in the visible on the Earth, that this technology of deploying solar panels would leave an imprint on the reflected light. So solar energy collectors, the large-scale deployment of solar power through solar panels will lead to a technosignatures. And this leads to the idea of something that's very important for us in the CATS collaboration, which is the idea of service worlds. Because what you might want to do is not actually put those solar panels on your own planet. You might put it on a satellite. You might cover half the moon in solar panels and maybe beam that energy back down to Earth or to your planet. So this idea that, you know, airless planets might, or worlds that are uninhabitable, you might put your industry or your energy collecting there. You might use them as service worlds, and it's the service world that you're going to be able to detect easily, not so much the inhabited planet. Okay, now one of the things, atmospheric pollutants are a lot of what we're interested in the CATS program. And here's a paper on looking at nitrogen dioxide as a signature of extraterrestrial technology. So there are a number of different kinds of technology that produce nitrogen dioxide. Here is a plot of all of the cross-section for different molecules included in the atmosphere, including nitrogen dioxide. And here's the result of using, again, LUVAR, and looking at the signal to noise ratio versus observation time. And what you see is after about 400 hours or so, you get to a signal to noise ratio. You get to an SNR of 5, enough to really claim a detection. So between 3 and 5 is the kind of where you're going to get really excited. So what this shows is that if there's enough atmospheric, or even this was Earth levels of NO2, you could in principle detect it with long observations with something like LUVAR. We also looked at this with CFCs, chlorofluorocarbons. This is a chemical which really, it's very hard to imagine how nature would produce. We used it quite a bit for a while. We stopped using it, but it's possible that someone could use CFCs. It's a great greenhouse gas. So if you wanted to say terraform, this is the kind of chemical you would use. So because it's such a great greenhouse gas, we actually ran climate models for various levels of CFCs, 1 times the Earth, what we have now, 10 times, 100 times, to look at how the climate would adjust to having the CFCs, and then used that planet as we observed, synthetically observed that atmosphere to look for the indication of the CFC lines. And so here is a plot of the lines from that. And so you see particularly these dashed lines here are the CFCs, and you can see how much they're changing as you go from 1 times the Earth level now, 10 times the Earth level now, and 100 times the Earth level now. And so what this led to is something that was quite important. It was a kind of milestone. So here's a plot of the signal to noise ratio versus transit time using JWST. And what you see is assuming that the noise floor is 10 parts per million, which is optimistic, we agreed that 100 hours of observation time on the JWST will get you to a signal to noise ratio of 2 for observing TRAPPIST-1e, if TRAPPIST-1e had Earth-like levels of CFC. With 5 times the Earth levels of CFC, you get to very, very strong level signal to noise ratio. So what was important about this is it was a milestone because it showed that Earth-like levels of a civilization could be detectable with Earth-like levels of technology, meaning technology we have now. And of course, this will get better with better telescopes. So it was important to show that we're already at the point where, if we were lucky, we could detect a nearby planet, the technosignatures from a nearby planet, with telescopes we have or we're going to have soon. Now, all of this systematic thinking was important because, as I said, it's led to a kind of renaissance in, all of these new studies in technosignatures are also allowing us to begin to think more systematically about all aspects of the problem. Many, I introduced in the history of SETI a bunch of different kinds of questions that were raised. Now, because we're finally getting a chance to really develop a community, we can examine those in new ways, give them new attention. And so questions like, is there really a Fermi paradox, right? Is there really a great silence? How common are technosignatures? What is the lifetime of technosignatures? What's the expected age of the civilizations we will likely detect? All of these questions have gotten new attention and a more systematic modern analysis in what's happening. So, for example, the Fermi paradox and the great silence. So there was a paper that Jason Wright led, really building off a paper that Jill did, which asked, how much SETI has been done and how much of the parameter space has actually been looked at. And there's this idea that sort of, every day astronomers are going out and measuring, are going out and looking for signals of intelligent life. That's the way the public sort of looks at it. And so, yeah, we haven't found anything, so therefore there is nothing out there. But nothing could be, that is so far from the truth. In fact, if the entire parameter space that SETI needs to search, if that was the ocean, how much of that ocean have we looked at? Basically a hot tub, right? So if you looked in a hot tub and didn't find any fish, would you then say, well, there's no fish in the ocean, right? Or if you pulled up a hot tub's worth of water from the ocean and didn't find any fish, would you then conclude that there's no fish in the ocean? So, that's really the important point that came from this analysis. There is no great silence. There is no indirect Fermi paradox because we just haven't looked yet. Another thing that has gotten more attention now is sort of thinking about technosignatures within the context of biosignatures. So this is a paper that literally just came out from the Katz group, and the title is "The Case for Technosignatures: Why They May Be Abundant, Long-Lived, Highly Detectable, and Unambiguous." So there's a claim, and it's kind of a natural claim. It's a prior, basically, that many of us go into thinking about technosignatures and biosignatures, which is like, look, there must be fewer technosignatures than biosignatures. And when there are technosignatures, they're probably short-lived. And why is this a prior? Because when we think about the evolution of life, and particularly when we think about it in context of the Drake equation, right? The technology part comes all the way at the end of the Drake equation. So we think that, look, technospheres, which would be, if we think of a biosphere as the sum total of biological activity on a planet, a technosphere is the sum total of technological activity on a planet. It must be that technospheres come last, so it's a shorter phase. So therefore, technosignatures must be more rare and more short-lived than biospheres. So here's a planet with only a biosphere. Here's a planet with a technosphere, right? It's got an space elevator and lots of space cities out there. And so the idea was that the number of technospheres divided by the number of biospheres in the universe, which in the paper we showed you could write in a Drake equation like way, must be much less than 1, right? That's the prior that we have. But in this paper, what we did is we went back and we looked at that. And the thing you have to understand in this is thinking about what I would call the triads of life and planets, right? So biological life goes on to produce biospheres, right? This sort of integrated, activity on a planet. And it's the biosphere which produces the biosignature. It's the large scale chemical imprint that comes from the biosphere that produces biosignatures. Now, technological life, we can do the same kind of triad for technological life, meaning a species that has developed technology. Technological life will develop technospheres, and it's those technospheres which will produce technosignatures, right? So when you think about these things as separate things, what you realize is there's a really big difference, which is that biosignatures need biospheres, and they need biospheres that still exist, whereas technosignatures don't need their technospheres to exist anymore, right? Or they don't even need to be in the same place as the technospheres, right? So here's a bunch of examples of technosignatures that we have launched into space that are no longer around. They're no longer associated with Earth's operating technosphere, right? So there's the Voyager probe, the Mars lander, or the Mars rovers, Pioneer, and New Horizons. These are all technosignatures. Now they're producing very small signals, right? Their radio output is very small, but as time goes on, you can imagine a technosphere pushing lots of these things out into space, and that there will be much stronger activity, much stronger detectable activity from these technosignatures. So what this means is a single civilization can produce many, maybe millions of technosignatures. Each one of these is a technosignature up here. So for example, Mars already has Earth's technosignatures beaming out into space, right? And more than that, the technosignature lifetime can be much longer than the technosphere lifetime, right? So for example, if the human technosphere goes away in another 100 years or so, the lunar lander is still going to be up there for a while, right? And imagine, this goes back to the idea of service worlds. Imagine that a civilization takes its moon and covers it in solar detectors, that civilization could end, but there will still be technosignatures there for a very, very long time. Now, this is not to say that, oh, we should be searching for technosignatures rather than biosignatures. That would be silly, right? Because we still don't know how prevalent technosignatures are. But it's important to sort of, what I want to do is I want to merge biosignatures and technosignatures, or see technosignatures in their rightful place in the activity which is the search for biosignatures. Technosignatures are a kind of biosignature. Okay, so in the last 12 minutes here, I want to talk about why does any of this matter? Because I think the most important part of this is that really carrying out this activity reflects back on what we're doing now, on human civilization now. And this has always been true, but it's particularly true because of what we're undergoing right now. And this is what I will call the astrobiology of the Anthropocene. Okay, so we have this problem that we all know about. Anthropogenically driven climate change is changing the planetary climate state from warm and moist, which is the Holocene, to, we don't know, right? And it could be, very detrimental to human civilization. The biosphere is going to go on. The biosphere is far more robust than we're going to do, significant damage to, but the damage is going to be to us in particular. So the question here is really sustainability. How do we achieve a sustainable version of human civilization that is also just and leads to human well-being? So this leads us to the idea of the Anthropocene. What it's been clear now is that human activity is become the major driver on the coupled planetary systems. It's human activity, which is both changing the climate, moving around huge amounts of material, moving around huge amounts of important elements like phosphorus and nitrogen. So we're entering this new geological era called the Anthropocene, or has been called the Anthropocene. And it leads to the question of, are sustainable versions of our kind of civilization even possible? This is the astrobiological view of this. And what I mean by that, does the universe do this kind of thing, right? We know that there's this cosmic inventory where the universe makes comets and it makes black holes and it makes, planets. But does it make sustainable, energy-intensive civilizations? Does it make this, or is that part of the cosmic inventory? And one way you can frame this is climate change a great filter? Is climate change, or are there other things waiting in the weeds, but particularly climate change, because that's what we're going through now, which can abruptly halt the continuing evolution of a technological civilization? Now, this is interesting because it modifies our understanding of a previous idea from SETI, which is the Kardashev scale. And you remember that Kardashev scale was the type 1 was you use all the power available to the planet from sunlight. So it was really an energy only view. But really the lesson of the Anthropocene is you can't ignore the biosphere. So really, in Kardashev's kind of conception, a type 1 planet was a kind of planetary brutalism where you just sort of brought the whole planet to heel with your amazing technology. And what we've learned is now you can't bring a planet to heel. The biosphere will have its say, but maybe you can bring it a plan, right? You can bring it a plan for, trying to become sustainable with the biosphere. And that's sort of the question of what I'll call the astrobiology of the Anthropocene. And what the response, the astrobiological response to this question is this. We now know enough about planets because of our 3 revolutions in astrobiology and how they respond to changes to begin modeling how any species would drive feedbacks on any planet via civilization building. So in particular, so this is what I'm going to call the astrobiology of the Anthropocene. And so what we can do is we can at least begin now to model how a civilization and a planet might interact. And an example of this kind of dynamical systems theory approach is from, it's where population biology came from, the predator-prey models, the Lotka-Volterra models, where you've got some bunnies and you've got some wolves, and you can model their interaction as they kind of feed on each other. Obviously the prey is eating the bunnies, but when the bunnies go away, then the prey dies. And you can take the same approach and try and model a civilization and a planet together to model how the civilization grows and how it feeds back on the planet. So we did this in a 2018 paper, and actually I wrote a Atlantic article for this. And we developed these equations. The first version of this was very simplified equations, where we had an equation for the population change. and then another equation for the planetary state, which you could think of as temperature. And then there was lots of parameters that went into this about like the planet's sensitivity, the response of the population to harvesting energy from the planet. And then and actually what's interesting about these equations, I actually took them from studies of Easter Island. People were trying to understand what happens, the Easter Island, one thing to understand what happened there was a kind of ecocide, that the population there was a nice isolated island and they ended up using all the resources they needed to survive. And that is what led to the dramatic drop. So I found a paper on that, and I kind of modified their equations to kind of think about, Easter Island for exoplanets. And so here's the results that we get from these dynamical systems models. So here's a bunch of different runs of our model for different parameters. In this, green is the population and red is the planetary temperature. That's the way to think of it. And what we found is there were 3 distinct classes of behavior in these models. First, there were die-offs, where the population rose very quickly by feeding off the energy of the planet. The planet's temperature responded because of the thermodynamic feedbacks. And then because of that, the population dropped precipitously, right? So there was a huge die-off. Now, technological civilizations are complex. It's not clear that you can lose 50 or 100% of or 90% of your population and still exist. But, at least, so these models, you didn't have the civilization go away, but it certainly sustained an apocalypse. Another possibility was, this was wonderful, we found sustainability. There were models, which I called soft landing, where the population grew, the planetary state changed, but you came into a new equilibrium. So that's kind of what we would be hoping for ourselves. And then, unfortunately, there was also collapse, where the population grew. It drove the planet into basically a runaway state, the planetary climate in a runaway state, and the population just dropped essentially to 0. So from these models, this question that I asked before, we could answer: are sustainable versions of our kind of civilization possible? Yes, but, right? In principle, they're possible as far as the models go, but there's also lots of examples of catastrophe. So this is sort of one way in which thinking about the problem astrobiologically may give us some insights into, what lies ahead for us. And then I'm going to end with this new paper we just put out, which was on the topic of quote unquote planetary intelligence. And here, what we were doing is we were using sort of the astrobiological view from the 3 revolutions in astrobiology to ask about the long-term evolution of technological civilization like our own. So this is a paper that we just published just earlier this year. The title was "Intelligence as a Planetary Scale Process." Myself, David Grinspoon, and Sarah Walker were part of this. And the press release that the university did for this, was "Can a planet have a mind of its own?" And I'll explain what I mean by that. And there was also, if you are interested, there's a Atlantic article that we wrote that just came out a month ago on this paper. So here's the question. SETI, like the last part of SETI, is intelligence, right? But who or what has intelligence? And conventionally, we see this as a property of individuals. Intelligence exists in brains, right? And brains sit on the shoulders, or what used to be shoulders, of individuals. But we already knew that, intelligence could also be a property of collectives, right? There's collective decision-making by social insects, the superorganisms that people have studied for a while. But it's also become clear that actually, cognition, in the sense of being able to respond to information flows, is something that exists in a lot of different systems. So slime molds, for example, can actually solve mazes. There is a certain way in which there's a collective decision-making happening in slime molds. There's bacterial quorum sensing, where bacteria will, as a community, will respond to the environment in ways that allow the community to persist. And most important, there is the discovery of the mycorrhizal networks of forest, the root systems that, the trees are not really what matters for a forest. It's the forest itself. What really is the living entity, or the organism, is the forest, and that the entire forest, stretching across hundreds of miles, is responding to environment. So there's been, lots of studies of this now, how if one part of the forest is undergoing a stress, the forest, through the mycorrhizal network, will send, it's my dog, stop, will send nutrients to that stressed part of the forest. Excuse me, I'm going to tell my dog to be quiet. Atticus, be quiet, please. Thank you. Such are the dangers of Zoom meetings. Okay, so our idea is that intelligence, broadly construed, we already know it operates across a wide variety of length and time scales. So is it possible to operate at planetary scales, right? And if so, how might a transition to planetary scale occur? And I'm not going to go through this in a huge amount of detail, obviously, because I've only got a couple minutes left. But the idea is, that the Earth, the way to think about the Earth is in terms of coupled system, Earth systems theory, or coupled planetary systems theory, where you've got the biosphere, the land, which is the lithosphere, the cryosphere, which is glaciers, hydrosphere, water, and atmosphere. And there's dense feedbacks between these. Particularly life is driving feedbacks between these. And as the life evolves, the feedbacks change. And so what we were looking at is how might cognitive activity operate in this system over time. And we thought about the different properties that we should have for this. And the one that matters, I just want to focus on, is what's called the autopoietic view. Autopoiesis is this idea that comes from biology that living organisms are self-maintaining and self-producing, right? That's what, that's sort of one of the hallmarks of a cell, is it manages under, all kinds of situation to keep creating the processes and products that allow those processes and products to keep going, okay, like the cell membrane. So our idea is that, planetary intelligence would be the capacity for these systems and their networks to respond to changes in a way that allowed the whole system to continue to operate. So this is related to Gaia theory and the work of Lovelock and Margulis. And so what we thought was that there would be that there would be transitions in a planet that would lead to this idea of planetary intelligence and self-maintenance would rise or fall depending on the evolution of the planet. So you might imagine stage one as being an immature biosphere, where the biosphere is new, it's quote unquote thin, and it's not yet exerting significant feedbacks on those geosystems. So this would be like Earth, perhaps in the Archean. But as time goes on and life evolves, you get much denser webs of feedbacks until really the biosphere hijacks the whole planet. This is, the kind of the Gaia idea. So the biosphere alters the geosystem's functions, and the Great Oxidation Event is a great example of this. And this is a mature biosphere where the planet has, the networks are doing some degree of self-regulation, may not be homeostasis entirely, but the networks have the ability to respond to keep the system operating. Now, the same thing could happen with technospheres, right? You could have, what we do have now is an immature technosphere. So we have a technosphere, we have these incredible technological systems, from energy to transport, information, bureaucracy, governance. So it's exerting feedbacks, very strong feedbacks on the planet, but they're unregulated. They're not really strongly coupled in a positive way to the biogeosystem. So that's us right now, the early Anthropocene. And what you might imagine if a civilization is going to be long-term, so that actually we would find it eventually, is that there would have to become a mature technosphere in which you would integrate. The technosphere would have to be integrated into the biogeosystem, the biogeosystems, so that there's feedbacks that to prevent the loss of self-maintenance. And that would be something that David Grinspoon called the Sapiezoic eon. That once you get to that point, now you can kind of exist forever. You've learned how to live on your planet. And now that civilization, may be able to endure, in perpetuity, or at least, for a very long time. Okay, so now my closing thoughts, I'll do this quickly. This field of astrobiology and biosignatures and technosignatures is both the greatest adventure and the greatest challenge, right? So technosignature studies, I think, they're just part of astrobiology, and we should see them as part. And astrobiology is now a robust data plus, as I'll call it, driven science. We're developing new instrument designs to do it. We're developing new statistical measures, new theoretical studies to do this. And it's so much part of science now that if you look at the last decadal review that just came out, astrobiology was a fundamental part of it. It's not, the search for life in the universe can no longer be thought of as being something that, to be laughed at. The astronomical community recognizes this is going to be one of our premier topics over the next few years, or next decades, actually. So now, in terms of the greatest challenge, what's so beautiful about this field is the way it just challenges your assumptions. Once you start trying to think about it systematically, you really realize all the ways that your biases as a human being, and perhaps a human being in a particular kind of culture, come into play. So I just want to show these two books because I have read *Sapiens*, and I'm now reading this book, *The Dawn of Everything* by Graeber and Wengrow, and they tell two very, very different stories about humanity. I encourage you to read them both. I'm not sure which one is true, but *Sapiens* has this sort of this view that we've heard before about, there was the farming, there was the agricultural revolution, and that led to, domestication, and that villages, cities, empires, technology. And then there's this new book where they really just completely challenge that and say that's not what has happened at all, and that there are much more variety. And this will play in terms of human civilizations and social organization. And this may play directly into when we think about technological civilizations, how they might organize themselves, and how that will lead to technosignatures. And then also, I recently, thanks to Jason Wright, was introduced to the indigenous critique of SETI. And there was a number of papers done by this where indigenous scholars were looking at SETI and really challenged SETI scholars to say, like, are you really thinking about what it means to be in contact with, another civilization, and what that means both for yourself and the other civilization? So these papers have really blown my mind, and I recommend them to everybody. So, all right, so that's it. There's lots of work ahead. I have to, of course, acknowledge Carl Sagan, both because, I got the Sagan Medal earlier this year. And, where would we be without Carl Sagan and his efforts everywhere in this? So I will end there, and I will just thank you. And I will also note that it's time to stop giggling about aliens. All right, so I'll end there, and I will stop sharing.
Wonderful. Thank you so much, Adam. Great presentation. Lots of thoughts and inspiration. Let's collect our thoughts into great questions, and we're going to be back in our 120 seconds after this little jingle is over. So audience, please submit your questions, and panelists, have a look at the great questions already in the Q&A, please.
All right, I'm ready for a nap now. No, kidding.
Hold off for half an hour. Okay. So thank you very much, Adam, again, for a very inspirational talk. This was really great. So I'm gonna start off with my first question as a warm-up. I'm gonna I want to take us back a little bit back to our planet, because we astronomers, of course, always, right, we venture out into the universe, but we sort of forget about what we're running on, right? And so I was actually hit by a thought once you started talking about this entire ecosystem and the intelligence of the whole planet. Have we actually looked deep enough? There was a flurry of papers and I think like articles a few months ago about missing like these geological discontinuities. There are whole strata apparently missing in our geological record all across the planet. And there is something that is called, if I remember correctly, the Silurian hypothesis, that we might have actually missed entire civilizations that were before us, present on this planet in some locations. Does your group actually look into this?
Well, it's good. I'm the right guy to ask that, because I was a co-author on that paper. It was Gavin Schmidt and I wrote the paper, the Silurian hypothesis paper, which is funny because the way that paper came about was Gavin Schmidt is the head of the Goddard Institute for Space Studies, a NASA climate institute. And I went there with my astrobiology of the Anthropocene idea because I needed help in the climate studies. And so I proposed this idea of like, well, what about climate change on alien worlds, which I thought he was going to laugh me out of the office. And instead he said, I said like, well, of course, we're the only civilization on this planet, but on other planets. And he stopped me and said, how do you know we're the only civilization ever on this planet? And I was like, my jaw dropped. And he's thought about this for a long time, about the Earth gets resurfaced, completely resurfaced after a couple million years, and the fossil record is not very complete. So if you had a civilization that lasted for say 100,000 years previously, which is very short on the geological timescale, how would you even know? There probably wouldn't be fossils. And so that paper, the exercise we went through that paper was just to ask, how might you know? And the only way you could really tell was by doing this kind of deep examination of the strata in terms of things like, looking for climate. Did they trigger climate change? Were there in the strata, were there things like artificial steroids or something, things that come from industry? Plastic, yes, micro particles of plastic. And the interesting thing is that kind of study's never been done. So you can't, it's not that we believed that there was another civilization, but we were just, the point was you don't know until you actually look, and nobody's ever looked along those lines. And so that was what was really interesting. So I don't think that there's, I don't think there's been another civilization before us, but it was interesting just to note that, because this also goes to the Fermi paradox too. So we've done a bunch of work of modeling the direct Fermi paradox, where a civilization crosses space, settling systems. And the question there is, well, maybe that happened a billion years ago. Like maybe there was a civilization that came through, settled Earth, had 100,000-year civilization, and then disappeared, right? That's a possibility as an answer to the Fermi paradox. And so, there again, this question of, well, how would you be able to tell? And it turns out it's not so easy. And you have to actually tune your studies, your I have such a hard time saying this, stratigraphic studies for those kinds of things. And it hasn't been done before.
Yeah, it's time to team up with the geologists, I think.
Yeah.
Okay, so many great questions here. Let's go to Franz next.
Great. Thank you very much for the very interesting talk, Adam. So, you kind of started off talking about several technosignatures, and I felt like they were aligned with the technology of today and the pollution of today and everything. And I'm not necessarily sure, well, there's a couple of things here, right? Like, in order to detect those on other planets, you said, oh, well, we need to scale them up by a factor of 10 or 100. And then we need exposures of 300 hours or 400 hours, which, good luck at, convincing a TAC to do that. You touched on this later on, was if a society gets up to, a scaled up point, right, where they're doing that, we probably expect them to develop new technologies or to be far more efficient in their use, right, to actually have a sort of cycle that works, right? They sustain a sustainability sort of thing. And so you kind of touched on that. What you didn't touch on was the alternative, which is, let's say that the society screws up and, to the point of self-extinction. And what biosignatures or technosignatures are there for that self-destruction, right? You know, would we see radioactivity, for instance, in the atmosphere, which would be kind of weird. Like, why would we see that? So maybe you could touch a little bit on the dark side of technosignatures.
The dark side. Yeah, there have been papers about this, about actually, some of the work on atmospheric pollution was, in fact, the first paper, I believe, was about, radionucleotides, the results of a nuclear exchange, that would actually persist long enough that you might be able to see it. So it's quite possible in those ways, and maybe other things as well, of civilizations ending. You might look at planets and have them look, very strange in terms of their atmospheric chemistry, in a way that they put things in that have long, you have to have, the problem there is you have to have long residence times in the atmosphere. But I think that would be something that would need to be, characterized. And that's my idea, that with technosignatures, we're really just finally beginning to get the process of being systematic about it. Because like I said, there's all these different things that have been proposed, and many of them are in the gray literature, or in conference proceedings from 1968. So, so now what you have to just kind of do is gather them together and evaluate, okay, which one of these are the ones we focus on? Because it's one thing just to say, oh, maybe here's something, right? Like, I'm very fond of the solar panel work. I think that, that's a really interesting, the idea of service worlds. I think that's a really interesting possibility. But okay, so that's a possibility. Now we've got to actually model, let's say, okay, so let's take a moon and cover it with 50% of its surface with solar panels. And now we've got to observe it from a distance. And what kind of signal do we see? And, what kind of modulations do you see in it? So that's what's really interesting, is to sort of we're beginning to sort through these technosignatures, propose them and sort through them, and decide which ones do we put the very long effort into in terms of actually characterizing them, so that when people are doing observations, right, people are, what's nice about this is people are going to be doing biosignatures, and many of these technosignatures will be in the same wavelength regime. So it's just like, what we want to do is give a library of possible technosignatures that people could look for, when they're already doing gathering their data.
Speaking with the probabilities, just to kind of finish up, would the probability of a self-destructive civilization be the highest?
Yeah, I mean, that's I think what's more probable, though, I mean, this is interesting. And this is, again, when the hardest part of this field, and this is why I showed the Graeber book, the Dawn of Everything, is that, this is the real mind-boggling problem. How do you imagine the million-year civilization? What happens to a civilization with 1 million or 1 billion years of evolution? Because one thing, a paper that I did with Caleb Scharf and David Kipping, that really David Kipping did and invited us on, was to do the Bayesian kind of argument for will the first civilization you see probably be, your age, younger or older? And overwhelmingly, it's older, as you'd expect, right? But how do we even begin to, without bringing all of our biases in, how do we think in an unbiased way about these very, very long civilizations? And so for that, we need to talk to anthropologists and archaeologists and historians. We can't just be astronomers reading science fiction books. Though talking to science fiction authors is something I actually am really interested in, because I think their job is to tell stories, right? And this is more than just, you don't want to make predictions for the future. You want to look at a fan of possibilities. So that's really, I think, the hard part. Putting a probability on exactly what you ask, I think, is going to take some work.
Excellent. So I think Michael is next.
Yeah, I'm going to sort of pick up on a thread that Franz had just touched upon, this question of very long-lived civilizations and how we make, thinking from the point of view of the Earth, how we would make that transition to that mature technosphere. You're thinking about the way humans operate, and we're so individual-minded, working in tandem, or how one would work in concert to get that self-regulation, and whether humans are capable of this. I think this is one of the big questions, and it ties directly into what Franz was talking about. I wonder if you have any thoughts there.
Yeah, I have. I'm thinking about this a lot. So, one thing about whether or not a civilization makes it or not may have a lot to do with its evolutionary heritage, right? So, as my limited knowledge of human evolution is that our last common ancestor we shared with bonobos and chimpanzees, right? And bonobos and chimpanzees have very different kinds of social structures, a lot of which they evolved because of the, how plentiful food was. And so, we are both very hierarchical, but we're also, we also have a lot of altruism, but we're not a hive mind. So, we're very social, but we're not eusocial the way ants or, naked mole rats are. So, is it better to be hive mind? Do hive minds do better at dealing with the challenges of developing a technological civilization? Because one of the things that I think, in this idea of the astrobiology of the Anthropocene, one of the stories that comes from this that I think is useful as we talk to people, or is that the idea is that there's a way in which you should have expected climate change, right? That almost any technological civilization will trigger climate change. And so when I say this very carefully, because I don't want people to beat me up, but on one level, triggering climate change was not our fault, right? We found oil, it was like, oh, it was really great, let's use it. Not doing something about climate change, or the people who are, purposely misdirecting our efforts on dealing with climate change, yeah, it's their fault for sure. But that any civilization that, develops technology and starts harvesting energy from their planet, there's going to be feedback. There's second law of thermodynamics tells you there's going to be feedback. So it may be the kind of, social structure that evolution gave you, which way may determine whether or not you're able to make it through this cosmic teenagehood. But I'll tell you what the feedback loops have to look like for the technosphere. So the idea of a technosphere, there's lots of papers on this. People also talk about the econosphere, that it's kind of become a self-perpetuating network in which human beings are part of, but we're not the sole constituents. And my daughter actually works in climate policy. And so my discussions with her have been really interesting. So, we know that there are biospheric feedbacks, right? So oxygen doesn't rise above, 23% or whatever, because if it did, then, more methane would kick in, which would eat the oxygen, which would bring it back down, or whatever exactly those feedback loops are. For the technosphere, a feedback loop would look something like this. Your financial system, which is this super complicated, complex, adaptive network, if you tried to build more, if you were an agent who wanted to build more coal-fired plants, your financial system would be like, no. We have feedbacks built into place that's just not allowed. Like right now, the financial system, if you said, I want to go get money to build a nuclear bomb, people would, the financial system, it's not in there. There's no place for it. There's feedback loops that keep that from happening. What we are trying right now, my daughter tells me about what's happening in the world financial systems. They're trying to build those feedback loops in it that, that's what the carbon net zero is all about, that companies are making pledges that they simply will not take on any new non-carbon neutral. So that would, in a really mature technosphere, there'd be zillions of those examples of feedbacks that just would never allow the self-maintenance and self-sustainability of this global system to be undermined. How's that?
Makes me think that Bitcoin is against us here.
Bitcoin.
Yes. Okay, so next up, Sarah.
Hi, Adam. Well, there's so many exciting biosignatures and technosignatures. I loved your survey of them. I work in detail on biosignatures, as you know, and I'm going to ask a question, but I'm going to give you my comment first, that it's tough.
Yeah.
One of the ones listed, isoprene, by the way, that was my team, and we proposed it as not a good biosignature. It's produced in tremendous quantities on Earth, as much as methane, but it's destroyed quite quickly. And its spectroscopic feature overlaps with methane. So it's not a great one. But anyway, every one we look at, and we're looking at every possibility, they always have some major negative on them. So I just wanted I think the question for the audience for you to answer is, what's your personal opinion after all this hard work on whether we can detect a biosignature or technosignature in the near future?
Yeah,
I think we all have our own answer to that, but maybe you can give your own personal short answer, because we saw this array of wonderful things.
Yeah.
But I don't know if you have hope for any of them soon.
Well, it depends on what you mean by soon. So
let me pick a number then, say 25 years. Let's call it 25 years.
I think 25, I think at the edge of 25 years, maybe. I think really what
I like that. Let's just pause for a second, okay? Because I really like that. I think it's really good to just put it out there.
Yeah.
Yeah, that it's a maybe, because there's so
Yeah.
many great things and we have to pass the torch on to the next generation. But for now, we're busy finding all the possibilities.
Right.
But the reality is a kind of a harsh one.
Right. But gravitational waves, I think, are the great example of this, right? I mean, so gravitational waves were proposed, in the early 20th century or mid 20th century. And then, the gravitational wave detectors, people were trying to do it in the 60s, right? And then LIGO gets proposed. My joke always with LIGO is that, my entire life from being a graduate student on, I sat in talks where people were like, LIGO, real soon, LIGO, real soon, 1990, 2000s, LIGO. And then 2017 or whatever it is, wow, they nailed it. And I think what I like to tell people is, we're just in the canoes. We're just pushing the canoes off into the water, to get started on this long voyage across a vast ocean. And so the idea that it may take 20, 30, 40, 50 years, people shouldn't, be like, oh, that's terrible. This is the most important question human beings have ever asked. The fact that we're even at the point where we can begin to think about gathering data is such a sea change that, you should expect something this hard to take that long. So yeah, how's that?
Yeah, that's a good answer. Thank you.
Okay, Abel is next.
That's a great talk. I wonder, is there any real chance of using the James Webb Space Telescope for trying to detect any signature at all? You mentioned CFC, but I wonder about the large integration times, if they are realistic, or are there also any current proposals or people thinking about proposing?
So the example I gave from that paper, Jacob's paper that we put out, was more to show that it was possible, right? JWST, as Sarah is saying, is going to be stressed to, find biosignatures. I doubt anybody's going to give us 100 hours to look for CFCs on Proxima B. But the point with the milestone was to show that it was in fact possible with 100 hours. And there are things that are going to get more than 100 hours. So I don't expect JWST to, I don't expect JWST to give us 100 hours to do this, but it was important to show that it's possible. And as time goes on, I think, we're going to see more funded, searches for, and especially as we have more, the next generation of ground-based telescopes, the next generation of ground-based telescopes, I think technosignatures will become part of the portfolio of telescopes. And of course, there's also the possibility that in looking for biosignatures, there may be, that's why we're producing this library, people may inadvertently find some technosignatures. But I agree with you that I don't think JWST is going to be doing anything with technosignatures like soon.
But what about if the telescope detects any biosignature at all? Will that motivate people to put hours for technosignatures?
I think that's a really interesting question, right? You can imagine that if we got really exciting results about a biosignature, that would just kind of put all hands on deck, and that technosignature proposals might be looked at more favorably once there was kind of a proof of concept that, yeah, you can do this for life. And then all kinds of life are now suddenly going to become amenable to investigation, including the technological kind. Yeah, that's a good point.
Thank you.
Thank you.
All right, let's go to Hans next. Hans, you're muted. Could you unmute yourself?
Now, am I online? Okay, hi. Very impressed by your talk and the many aspects that you touched upon. You also touched upon the origins of life, coming back to the origins, and mentioned the concept of autopoiesis. And you mentioned Lovelock and perhaps others. I wonder whether you are aware of the Chilean biologist and philosopher Humberto Maturana and Varela, who actually published this book, The Tree of Knowledge, which is not easy to read, but has this concept of autopoiesis. And another book, since we are talking about books, Harari and Kramer, Another book which I think is interesting to read is a book by François Rodier in France. It's called The Thermodynamics of Evolution. Also a very interesting book. So I'm just wondering whether you have some comments on these and other publications related to the origin of life.
So Francisco Varela is one of my heroes, one of my great heroes. I never had a chance to meet him, but I read his work. I became aware of his work about 15 years ago, and since then have been we read a lot of his stuff. He was so far ahead of his time. It's really remarkable. I think in many ways the world is catching up to Varela now. And I've been lucky enough to participate in what are called the Varela symposiums at the Upaya Zen Center. Because Varela was very interested in sort of the Buddhist perspectives on life, and so there's always been this interesting dialogue between the Dalai Lama and neurosciences and such. And it was Varela who actually who started it. So autopoiesis in particular, I think, is a really, really interesting idea. And that's the reason I included it in that list of characteristics, was that I think it captures something about life that is often missed. So, when people talk about, the characteristics of life, there's often, as it should be, a big emphasis on reproduction and heredity and everything. But, what autopoiesis focuses on is just that living systems endure until they don't, right? And that they have to maintain their own self-organization in the midst of, difficult times. It's always difficult times for life. And so this idea of self-maintenance and self-production, with the cell being, the cell membrane being a clear example, I think is very important for us. It's a very rich idea for thinking about the life, the origins of life, the evolution of life. And there's another idea there, which was, I flashed that slide too quickly, but one of the things that we said is that, planetary intelligence would be a network. We'd have to think about it in terms of network theory. We'd have to think about it in terms of networks of information. And most importantly, the kind of information we have to think about is semantic information, which is different from syntactic information, the Shannon information that we're used to from information theory. Shannon was quite clear that there's nothing in here about meaning. This is just probabilities. But what life has to use that portion of semantic information, which is meaningful to it. So like in the example of chemotaxis, a cell has to be able to detect the sugar gradient and move up the sugar gradient, because that gradient is meaningful to it. To the rest of the universe, it's not. It's just, you don't really need the information perspective on that sugar gradient for anything else. But if you're living a system, you do. So semantic information is another, and Varela was very aware of this. And so now actually I'm working with a group from the Santa Fe Institute, Artemy Kocheski, young information theorist, to try and develop a theory of, that's something he proposed, on semantic information. And I think there's a Templeton grant, which I'm hoping we're going to get, to look at exactly that. So I think Varela's idea about, go ahead, I'm sorry.
Is he still alive, Varela?
No, he died in 2001 of liver disease. Yeah, at 60, really? 61, I think. Really tragic, because there were a lot of ideas. And like I said, the world is finally just catching up. He was so deep in ideas of network theory and autopoiesis, and it's now that these ideas, because it's interesting when I look at the history. If you look in early 2000s, people are still like autopoiesis, this is some kind of hippie stuff or something. And now what you find is people like David Krakauer at the Santa Fe Institute are using autopoiesis as kind of their foundation for understanding identity in biological systems and all kinds of other things. So like I said, the world is catching up to Varela, and it's a shame that he's not here to see it.
Thank you very much.
Okay, let's go to Joel next.
Hi, thanks for a great talk. However, there's something that you didn't talk very much about that I'd like to ask you about.
Sure.
How unusual is Earth is the basic question. So I've heard a lot of interesting stories from colleagues. For example, Konstantin Batygin and Greg Laughlin, who used to be at Santa Cruz but is now at Yale, had this idea that one of the reasons that our solar system is unusual in having rather light rocky planets, no super Earths, as you mentioned, is that Jupiter may have moved inward to about 1.5 AU and then moved back outward through an interaction with Saturn. Then there was the Earth proto-planet collision that produced the moon and made Earth lose a lot of volatiles. And then there may have been another reorganization of the solar system with Jupiter and Saturn causing the outer planets, Uranus and Neptune, to exchange, leading to a great bombardment, the late Great Bombardment. All of these things I understand are somewhat controversial, but the basic question is just how unusual does all of these things make Earth? For example, if Earth hadn't lost all those volatiles, maybe it would have too thick an atmosphere, too much CO2, and be too much like Venus, and therefore never really habitable. My own work with Francis Nimmo and Enrico Ramirez Ruiz and others was to show that Earth is a Goldilocks planet from the point of view of having just the right amount of radio heating due to uranium and thorium. The amounts of those vary quite a lot from star to star, and therefore from planetary system to planetary system. And the reason that they vary so much is that we learned in 2017 from the LIGO Virgo detection of a nearby neutron star merger, that these neutron star mergers produce enormous quantities of these so-called R-process elements, but they're extremely rare, only a few per million years in a galaxy like ours. So that tells us that the R-process contamination is probably pretty variable, and it seems that it is. So basic question, going back to a Drake-type equation, just how unusual is Earth and how much difference did that make in its habitability?
Yeah, that's the $64 million question. And I'll give my answer, and I'd like to open it up and see what other people think. We have a number of experts here. On Tuesday, I would say that we're so rare that wow, there's just so many coincidences. This is never going to happen again. And then on Wednesday, I'll be like, well, we do have, like I said, there's 10 billion trillion, habitable zone planets in the observable universe. That's a lot of possibilities to let these things happen. Of course, having it happen one time in some, planet in the Centaurus supercluster, is not as interesting as having it happen enough that there's something nearby. But I understand the question. There really seems to be, what's interesting here, and then I'll open it up and see what other people think, is that on the one hand, I think for just for microbial life, and this was part of the Rare Earth book, the Don Brownlee book, right, was that it's probably easy maybe to make microbial life because that seems to be quite robust and easy to do. But, animals may require something much more. So it's maybe
an atmosphere at least.
Yeah, right. It may be that really you need something, but what this leads to though is the question, as I said, with technosignatures, that if you just get one or two technospheres, they can seed the whole rest of the galaxy if they last long enough.
The Fermi question.
Yeah, right. So I think it's sometimes when I hear things about Sarah and I are part of this Center for Matter at Atomic Pressures, where one of the things they're using giant lasers to look at the equation of state, the interiors of planets, like super Earths, and ask whether or not you could have properties that would allow for plate tectonics. And maybe plate tectonics is so rare that it's impossible to get the kind of life we have, because plate tectonics seems to have been important for us. So I'll end there, and I would love to have other people chime in and see what people think.
Anyone?
Sarah, can I ask you, what do you think?
Well, of what topic specifically?
Of how do you think that how rare do you think the Earth is in terms of its history and what's happened on it?
I mean, I don't think we have enough information to, say anything about that.
Good scientific answer.
Yeah.
Pavel had
I have a comment.
his hand up. Let's go to Pavel next. Pavel had his hand up.
Yeah, I didn't want to jump the queue, but I would have a very pessimistic view on on the amount of life, I mean, intelligent life out there, and the argument which I see is that life is aggressive. It has to be, right? I mean, as soon as it starts, it will spread. It has to, because it will spread wherever it can exist, unless some other predator stops that particular one from spreading. And we see that also the great example of the Polynesians. Basically, there's no island on this planet which hasn't been settled by humans. So once one reaches the threshold of technology where one can actually reach out to other environments, I mean, to other places which can sustain one, then those will be reached and colonized. And so the fact that we do seem to be alone, I think, is very worrying. It makes me think that we are probably indeed alone, because if we weren't, then the whole galaxy would already be teeming with life. I think that's the general statement, but I think I don't see any argument against that. And yes, I think the Earth seems to be extremely rare, right? I mean, the Walter Bade, Dietrich Bade makes the point in the question and answer part here that there is the moon, which was just now also raised, and the early loss of the atmosphere, so that the Earth wouldn't have had too thick an atmosphere, and that alone, so not only having a planet in the habitable zone, but also having that type of event, which actually made that habitable zone planet sustainable for liquid water for a long time, and I think that's just so rare. And if you look at the emergence of our species, it's just so incredibly, unbelievably rare, right? The East African Rift Valley, which opened up and apparently enabling the hominids to just cross the threshold to become tool making. What's the chance of that happening? And if that hadn't happened, would have we had tool-making hominids and all that? I'm sure that the Drake equation seems to try to factor all of that in, but just from observation, it seems that by the mere fact that life is very aggressive, it has to spread. Otherwise, it would falsify its own sort of existence. And the fact that we don't see anything out there apart from us tells me that we are quite alone. Nevertheless,
I just do want to interrupt.
But it's still very important to test this hypothesis and to try to falsify that, because obviously finding some other technological civilization out there, or even remnants of it, would be potentially the greatest news ever, right? So it's indeed extremely important to search and look as hard as one possibly can. Personally, I'm just extremely pessimistic.
I'm pessimistic too, but I feel compelled to put a more positive spin after hearing you. So, yeah. I mean, what I like to say is, we'll know some things in time. We can't find another Earth around a sun-like star right now. We have no way to do that. People are trying. And so what if we imagine, 1 in 50 sun-like stars, even 1 in 20? We don't know the answer to that. Jupiter is also very hard to find. So I'm not here to talk about intelligence or whether other civilizations can get enough energy to travel and, go to another world. But I think we can make small steps forward in time. But as we were discussing with Adam, this could be like 50 years before we get our Habex or LUVOIR to find out if there are other Earths out there. Second, I do hesitate to speak outside my area of expertise, but I wanted to relay to you an amazing talk I heard. This is like 25 years ago, before exoplanets. It was an evolutionary biologist, was a grad student at Harvard, and he was supposed to be giving a talk on how to give a good talk, but he ended up rambling only on his own topic. And he wanted to try to argue that we had 5 chances on Earth. We had 5 independent continents for intelligent life to arise. And there's this argument how every ecological niche is filled. There's anteaters with long tongues here. There's like marsupials that do the same. So I don't know if that helps you feel a tiny bit, you or anyone in the audience feel a tiny bit more positive. We're not going to say it's 1 in 5 based on that, but there's some chance.
If I could also I want to point out though, but that you're still repeating the the great silence idea, which is wrong. We haven't looked. We have not looked. We have looked at a little teeny tiny little sliver, and so we just can't say whether or not there's, whether or not the galaxy could completely be teeming with life. We simply haven't looked. It's just the amount of space, of parameter space we've looked at is minuscule. So,
but the Earth is a prime estate. The life out there would come here.
What if it came a billion years ago?
Yeah, it doesn't matter. It would still be here because it's prime real estate, and that sort of resource would be used. And it's
a lot of people think that the intelligent life did come here. The Great Pyramids, the ancient aliens. I'm just joking, but people think it did happen.
No, but I just want to point that's one of the things I've learned is that there's just a huge number of assumptions about how civilizations behave and what, in that. And that's been the great thing about what I've been learning. Because I would have said that, 5 years ago. But now as I've sort of been forced to kind of talking to anthropologists, talking to, people who sort of looked at just even human civilization, there's just this enormous diversity about groups. That's why this whole narrative, I showed you the sapiens thing, that narrative of human beings spread after the agricultural revolution, it turns out that's not at all what at least that's what the Graeber and Weber would say. There's been an enormous diversity of human social organization, oftentimes deciding not to expand, for their own reasons. So it's really, I think it's really a great opportunity for us to rethink some of the narratives that we've been given by our own culture in many ways.
Yeah, but you see, the thing is, it might be true that one or the other culture decides not to expand, but there will always be some culture which will expand. And that's how it has been in history, right? And you can see what's happening on the planet right now.
Yeah, right.
Right. So, yeah.
Okay. Paul had a question, so let's go to Paul. I see Hans is waving his hand, but Hans, can you hold off? Paul, please go ahead.
Okay, thank you. That was a wonderful talk. So informative, so many interesting things. I had two slight forms of uneasiness. One is unavoidable, that so much is so hypothetical and speculative. But that's unavoidable. I mean, the alternative is just shut up. And that's not a good idea, because in this way, we can discover, I mean, much is heuristics, and then we think about it, and then we may discover things how to test them then empirically, and without thinking about the possibilities of empirical tests, we don't go anywhere. And therefore, that's unavoidable. And if for some people that may be too speculative, so they should go to other conversations. That's fine, but that's something, it's some sort of uneasiness for me. Also, with that Maturana Varela stuff, I'm not so easy about it. So anyway, but that's a normal thing. The other thing is something more subtle. It's not really in the center. This is when you talked about this astrobiology of the Anthropocene. And at first sight, I thought, oh, that's a wonderful idea. So we can make that useful, right? So we can use this astrobiological insights to solve some problems here on Earth. But I think that's a little ambivalent, because what is happening here is that you then, in some sense at least, you justify that sort of astrobiological research by its usefulness, for us humans. Finally, perhaps even economically. And I'm very critical about that in general, because that's the normal way how so much is done, is argued for financial support of the sciences, by its usefulness. But we shouldn't rely on that exclusively. We should always say it's a part of culture. It's part of our curiosity. It belongs to us as human beings. We want to understand what's going on. And we should, and I mean, in all countries, United States as in European countries, I mean, the favorite mode of arguing, even for basic research, is, oh, it'll be useful, technologically, economically, blah, blah, blah. We can solve this and that problems, which may be right. But the point is, in our culture, especially, I mean, for you astronomers, it should be very important that you keep stressing this is part of culture. It's like opera. It's like beautiful gardens. It's like keeping some biological diversity somewhere. It's not useful for anything. It's just because we are human beings and this is part of our culture. And so there is a little ambivalence with that argument, the usefulness of astrobiology for the Anthropocene. I would try to balance that with the constant stress. We are doing science. of course, also because of its usefulness, but an important part for the basic sciences is our human beings who are curious where we are, what we are, where we are going.
Yeah, I think that's a really interesting point. And you know, the first part about the speculation, absolutely. I mean, that's just, what are you going to do, right? So for some people, this is not going to be fun. They're not going to want to do this because it's too much speculation, and that's not the way they want to do science. And I completely understand that. But again, if you look at astrobiology, right, which has made, you know, so much progress, people will say, oh, you know, astrobiology, it's an n=1, you know, science. But to take that point would be to miss all the ways astrobiology has changed our understanding about life and planets, even with just n=1. Because we do have Mars and Venus to look at in terms of climate change. You know, both those planets experience climate change. And we, you know, so we've got an understanding of how planets themselves evolve. And then we've got all the different examples of, you know, the life on Earth, how, you know, Earth and life has evolved. So, I mean, you start off speculative, and then hopefully, you know, if you can systematize, the first step is to systematize how you're thinking, and then that can lead to something more specific. So for example, like the work we're doing with the CATS grant, where we're actually developing this library of chlorofluorocarbon, you know, technosignatures. What spectral band should you be looking at, and, you know, what kind of strengths should you look at? So that's very hardcore grinding away at an atmospheric model. Your second point, though, I mean, when I propose the astrobiology of the Anthropocene, I'm not looking to like see it as being like this is going to help, it's going to help funding or anything. Because I just don't, yeah, it's too far from that. But what it does help, and this is what I've used it as a science communicator, as a scientist who does a lot of stuff for, you know, CNN and New York Times and such, the narrative that astrobiology gives us, that is what is powerful. It is a way, you know, I've been writing for the public for 20 years. And when I was working for NPR, I had a, you know, weekly column, and I wrote about climate change a lot. And I watched this rise of climate denial, you know, where, you know, I would write something about climate change, and there'd be a couple of, you know, people saying, oh, you scientists, it's all hoax. And then as the year went, you know, 2008 to 2009, 10, it started to become a flood. If I did anything about climate change, there was this avalanche of stuff in the comment section showing me that there was a really organized science denial. And the story of that they would tell each other was one that I think the astrobiological narrative, it just turns it on its head. It completely subverts the climate denial narrative. One of which, right, is that you know, is climate change happening? Do scientists really know that climate change is happening? From the astrobiological perspective, that question doesn't even come up. It's like, of course it's happening. You built a world-girdling civilization. What did you expect to happen, right? And then this sort of, because it's often coming from, you know, it's often projected as a business versus, you know, ecological argument. You know, the astrobiological narrative also flips that, because it says, look, triggering climate change is a measure of our success as a species. You know, like, wow, you know, a bunch of hairless monkeys managed to like change the atmosphere of an entire planet. Wow. Now, are you smart enough to do something about it? So, you know, I was on like the Joe Rogan show, for example, and the Joe Rogan, you know, that audience, there's a lot of climate denial-y kind of people on that. But I got a huge feedback, positive feedback, that people were like, oh, this is the first time I've ever been able to think positively about climate change. Because it's this narrative about climate change that we're locked into, right? That it's just, you know, people just can't get past the polarities. And I think the astrobiological perspective just gives you an entirely different way to talk about the story, and that can give us a kind of path forward to actually take action, about why we should take action, why it's imperative to take action. So that's what it's been for me.
Hans.
Okay, let me come back with my final comment on the rare earth hypothesis you mentioned, Brownlee, and there is a more sequel to that book by André Meder, which asks the question whether the earth is unique given astrophysical factors. There are so many factors for life to be sustained on planet Earth. Could be like 10, let's assume 10 factors. If each factor has a probability, and these are independent probabilities, like 10 to the minus 1. So with 10 factors, you're easily down to 10 to the minus 10. So this shows that with very simple assumptions, kind of a lottery, you are easily in the range of one or a few live species in the galaxy, at least. So I don't want to challenge your pessimism line of 10 to the minus 22 for a civilization to ever exist in the universe. But in the galaxy,
Yes.
you can easily make a statistical argument that it cannot be very frequent. Do you agree?
Well, I mean, what's interesting is now, since all the astronomical terms are nailed, the only terms that are open now are the biotechnological ones. And so then you're going to have now have 10 to the minus 3, 10 to the minus 3, 10 to the minus 3 to get you, or more for those in order to get you to the point you're saying. But I agree in principle. It's possible that the galaxy is currently unoccupied other than by us. But
well, it could be few. There could be few, but and I don't know whether Pavel agrees that if there are few, then we would have seen it.
Right.
I wonder. I'm not sure. I mean, as you said, on a Monday or on a Tuesday, you think like this. On a Wednesday, you think like another.
But here's what I do think. I think there's good arguments that life, not intelligent life, not technological civilizations, life in biospheres may be more common. And to me, like, if we find another biosphere, that's fine. I'm like done. I don't need technological civilizations to feel like my mind has been blown, because life itself, life is such a different physical system, right? There's nothing else in the universe that is like life in terms of what it can do. So to know that it has happened even one time somewhere else means that, I think the universe will be full of it. There will be places, even if it's not our galaxy, where it's gone on and done interesting things. So all I need is a biosignature. And I feel the philosophical imperative has already been fulfilled,
But I doubt it's very frequent.
But I think I'm much more hopeful about biospheres. I think biospheres may be, but microbial life, I think the extremophiles show that it's microbial life is very hardy. So, yes. But yeah, I agree. I mean, again, until we find.
Thank you.
I'm being reminded by your discussion here that I asked the question, I think it was Sarah who I asked the question in her golden webinar, that we may actually not be looking at the right parameter space. Like, do you think that there is maybe the possibility that we are missing, sort of like a switching on of entire galaxies? Once life forms anywhere in a galaxy, it's basically polluting the galaxy within a few, 10 to 100 million years. And so we should be looking actually at lit up galaxies than individual stars in our galaxy.
Well, Jason Wright's been doing studies looking for type 3 civilizations. They've already done some the H-hat study. So they've begun that process of actually moving beyond the Milky Way and looking at other galaxies as per example. So I think that's a great idea, and that's something that absolutely should be studied. Let's look at galaxies to see which perhaps they are better places to see.
Exactly. Wasn't there like this flurry again of papers like a few years ago, like these red spirals that no one really could understand?
Yeah, I'm not familiar with. I believe I've only heard of that, but same thing. Yeah.
All right. Okay. Pavel, very, very brief, please.
Yes, just searching for a possible other technological civilization is also an issue of self-preservation, right? I mean, we would like to know if there is something out there which could potentially be a threat, which usually, looking at what's happening on Earth, would be the case. So that's really, I think, an important reason to really keep looking. And I was then going to ask something which maybe the panelists also want, or the speaker might not so much like, but the question about Oumuamua.
Oh my God! Gotta go. See ya. I mean, the stuff I've read, Oumuamua is super interesting on lots of different levels. It's certainly the idea. It's interesting from the panspermia point of view, and it's potentially interesting as a technosignature. I don't think that, the data is convincing that it was a technosignature. There's just kind of, for me and what I've read, when I read other things, the non-technosignature arguments, I find those to be compelling enough that I wouldn't jump on that. So, but in the future, that is absolutely something to look at. I mean, I think that's going to be I did not talk very much about solar system objects, things inside the solar system, including the lurkers, which is a really interesting idea. But in the future, Oumuamua woke us up to the possibilities that we should be looking for things that are passing through.
All right, the very last question from the Q&A by Simon.
Yes. I picked a question from Edgar Castro that says, are you in favor of sending signals so that other civilizations can detect us, or would you rather not?
I do not think we should. I am not an advocate of METI for a number of different reasons. One, which is like kind of what Pavel said, who knows whether or not there are wolves among the stars. You shouldn't go. I would not necessarily advocate announcing our existence. Yes, we've been leaking signals for a long time, but that's different from beaming and then reading this the indigenous critique of SETI, where they really they said, you guys have not looked at your history or thought deeply enough about what happens when civilizations come in contact. And the idea we're just sending signals, we don't expect to hear anything. That's not enough. There's been enough history on the earth that you really need to think deeply and have consensus before somebody just volunteers and says, oh, I'm just going to send a message. I know it's contentious. That's kind of my gut reaction.
And just a yes or no answer. Would you then be in favor of shadowing the Earth, obscuring the Earth?
I don't know if I'm that pessimistic. Pavel, I don't know. Pavel, that sounds like Pavel might be. But yeah, I don't think we, but as they say, just because you're paranoid doesn't mean someone isn't following you. So, who knows? But yeah, no, I don't think that's, at this point, I don't see that as being necessary.
Good. Thank you.
Wonderful. Okay, so let's wrap this up here. Thank you so much, everyone. Thank you, Adam, for a beautiful presentation and a great discussion. Thank you, panelists, for tuning in. Great questions. It was really wonderful. Thanks to the audience for tuning in as well. Please be so kind and fill out the survey after the live stream is over, and we will be announcing the next Golden Webinars series very, very soon. Okay, so stay tuned in our social media. Please follow us and recommend us so we can continue. Thank you, everyone.
Bye, everyone.
Bye-bye.
Thank you so much.
This was a really fun discussion.